Hello guys, I'm Matthew Cruz, and today I'm going to explain to you what is convection current, plate tectonics, and continental drift.
But first, let us know the layers of our planet: the inner core, the outer core, the mantle, and finally, the crust.
Now, let's talk about the theory of continental drift. You may have noticed that if you look carefully at the continents, the giant land masses covering about 29% of the Earth. If you look at them carefully, you may notice that they almost look like a jigsaw puzzle, especially if you look at the certain parts of South America and west coast of Africa. This has been already observed 100 years ago. There were some scientists who became interested with this discovery. Let me introduce to you Alfred Wegener. Alfred Wegener is a meteorologist. As a scientist of the atmosphere, Wegener spent almost all of his time looking at the maps, and he also noticed this strange shape phenomenon that the land masses looks like they were puzzle pieces separated by water. He spent his whole lifetime studying and trying to discover the mystery behind this. He believed that the continents were actually once a supercontinent, which he called Pangaea, about 250 million years ago. This is what he have thought it would look like. Wegener knew that if he wants to prove in the public, he must make his statements believable, so he came up with these four pieces of evidence. The first evidence that he came up with was already discussed. It's simply the observation that the continents appear to fit together. Wegener believed that there was a reason behind the shapes of the continents and that they did not just appear randomly. So this becomes the evidence number one, the apparent fit of continents. Wegener became quite interested in fossils and other prehistoric evidences. He had discovered that there were many fossils that can be found on separate continents. An example of this is the Mesosaurus, a freshwater crocodile-like reptile that lived between 286 and 258 million years ago, are found solely in eastern coast of South America and western coast of Africa. It would have been possible for the Mesosaurus to swim between the continents, since Mesosaurus can stand in salty water. This suggests that South America and Africa were once joined from 299 to 251 million years ago. So that's our evidence number two. We call it fossil correlation. He also became interested by rocks and geologic structures. He found out that the mountain ranges in the northeastern United States and the mountain ranges in the northern eastern Europe have the same composition. They have the same type of rock and the same age of rock. This means that these mountains were actually once together, and as the continents move, these mountains separated from each other. This becomes our third evidence, rock and mountain correlation. Identical rock formations and mountain structures have been found in separated land masses in the world. As a meteorologist and geologist, Wegener studied paleoclimate indicators in sedimentary strata. He found out that the upper Paleozoic strata in northwestern Europe contained extensive coals. Coals can only be found in a tropical climate. Coal deposits can be also found in Antarctica, northern United Asia, a southern tip of Africa, Australia, northern United States, which are not in tropical climate. The coal deposits in these areas is a clear evidence that these areas are once in a tropical climate. This becomes the fourth evidence, the paleoclimate data. The observation that coal has been found in cold areas. So these are the four evidences that Wegener had come up to support his claim that the continents are moving. What is convection current? The inner core of the Earth generates huge amounts of heat energy due to radioactive decay. The second law of thermodynamics states that over time, differences in temperature will tend to equal out or reach equilibrium. This means that the heat generated in the inner core travels out through the outer core and to the mantle, where it is much cooler as the bottom of the mantle heats. The viscous material that makes up the mantle moves the hotter material at the bottom of the mantle moves towards the top. Here it begins to cool down as heat is lost to the crust. The cooler material at the top of the mantle starts to sink to the bottom. Here it warms up and then moves towards the top again. This cycling of hot and cool material is called a convection. Constructive plate margins. A constructive tensional plate boundary happens where plates move apart. Most of these plate margins are under the oceans. As the plates move apart, magma rises from the mantle to the Earth's surface. The rising magma forms shield volcanoes. Next is, I'm going to explain destructive plate boundaries. As the name suggests, one of the plate boundaries where one plate goes under another plate or collide with each other and gets consumed or destroyed in the process. Subduction zone and suture zone are the example of destructive plate boundary. There are three kinds of destructive boundary or subduction zones: ocean-ocean subduction, an oceanic plate subduction under another oceanic plate, ocean-continent subduction, an oceanic plate abducting beneath a continental plate, as oceanic plate is heavier. Continent-continent collision, two continental plates collide and form a suture zone. Now, in ocean-ocean and ocean-continent subduction zone, the water mass over oceanic plate goes deeper down the trench. As a result, the melting temperature of the subsurface mantle material beneath the overriding plate, which is not going down, plate gets down, geothermal becomes depressed and magma is generated. This magma comes out of the overriding plate in form of arc volcanism.